If you spend enough time around web applications, you start noticing that breaches and near misses tend to rhyme, even when the technology stacks look different on the surface. What changes is the branding, the cloud provider, or the framework, but the underlying failure modes repeat because humans and organizations repeat. The value of a curated set of common risk patterns is that it gives us a shared set of mental buckets for what goes wrong most often, not in theory, but in practice across many environments. When you internalize these patterns, you get faster at recognizing what a system is doing, where trust boundaries exist, and which decisions are likely to create the next incident. A useful way to think about these categories is as a map of recurring weakness types, not as a checklist of specific bugs. The goal is not to memorize names and move on, but to understand the kinds of engineering and operational habits that produce the same outcomes repeatedly. These categories are intentionally broad because a single weakness pattern can show up as dozens of different technical manifestations in different languages or architectures. That breadth is not a flaw, it is the point, because it helps you generalize from one incident to another without needing the same exploit payload. If you can classify a problem correctly, you can often predict what adjacent problems are likely to exist in the same codebase or organization. This organization is also helpful because it forces you to separate symptom from cause. A single incident might look like data was stolen, but the cause could be missing authorization logic, weak session handling, unsafe defaults, or a dependency that quietly introduced a known vulnerability. Categories let you connect the observed outcome back to the engineering reality that created it, which is exactly what you need when you are prioritizing remediation or designing controls. Another advantage is communication. When teams share a vocabulary for common web risk patterns, discussions stop being vague and become about specific failure modes. That shared language is one of the most practical risk controls you can deploy, because it reduces misunderstanding during design reviews, incident response, and audit conversations. Let's start with broken access control, because it sits at the heart of many web application compromises. Broken access control is fundamentally about authorization, meaning the rules that decide what an authenticated identity is allowed to do within the application. People often conflate authentication and authorization, but they are distinct problems. Authentication proves who you are, while authorization determines what you can access and which actions you can perform. When authorization checks are missing, inconsistent, or implemented only in some places, attackers can reach functions and data they should never touch. Overly broad privileges are the other side of the same coin, where accounts and roles exist, but the permissions are so expansive that a compromise becomes catastrophic. In practice, broken access control shows up through patterns like direct object references, where a user can guess or manipulate an identifier and retrieve another user's data. It also appears as role confusion, where a regular user path and an administrator path share the same backend method, and the authorization guard lives only in the user interface layer. Another common pattern is enforcement that happens only in the client, such as hiding buttons or menu items, which is not enforcement at all because an attacker can craft requests directly. You also see broken access control in multi-step workflows, where the first step checks permissions, but later steps assume that the earlier check happened, and those steps can be invoked independently. The unifying idea is that the server side must evaluate authorization on every sensitive request consistently based on a reliable identity and a reliable policy. Now, move to cryptographic failures, which is a category people often misunderstand because they think it only means use encryption. Cryptographic failures are about weak protection of sensitive data, and they include misuse of keys, misuse of algorithms, and misunderstandings about what cryptography actually guarantees. Encrypting data at rest is helpful, but it does not matter if the key management is weak. The keys are stored next to the ciphertext, or the application leaks plaintext in logs or error messages. Similarly, encrypting data in transit is foundational, but you can still fail cryptographically through weak configuration, deprecated protocol choices, or improper certificate validation. This category is also about choosing the right cryptographic primitive for the problem, because hashing is not encryption, encoding is not encryption, and secrecy is not the same thing as integrity. Key misuse is a recurring story in breaches because key material is often treated as a configuration artifact rather than as a sensitive asset with a life cycle. Hard-coding keys into source code, reusing keys across environments, or using the same key for multiple purposes all increase blast radius. Weak randomness can undermine everything because session identifiers, tokens, and cryptographic nonces rely on unpredictability, and predictable values turn strong algorithms into weak systems. Another cryptographic failure is neglecting authenticated encryption, meaning you encrypt data but do not protect its integrity, leaving room for tampering that is not detected. Even when teams use strong algorithms, failures happen through operational shortcuts like disabling certificate checks in development and letting that behavior drift into production. The control message here is that cryptography is an engineering discipline that depends on correct selection, correct implementation, and correct operational handling. Injection is one of the oldest categories in web security, and it remains relevant because it is fundamentally about how software interprets data.
Injection occurs when untrusted input is treated as instructions by a downstream component, such as a database engine, an operating system shell, or an interpreter for a query language.
The classic case is structured query language injection, where user input becomes part of a database query in a way that changes its meaning. But injection is broader than databases, because any boundary where a string is parsed as commands is a candidate, including directory services queries, lightweight directory access protocol filters, command line calls, and even template engines. The problem is not input contains bad characters. The problem is the system mixes data and instructions and then trusts the mixed result. The most effective mental model for injection is that the interpreter is the danger zone. If a component parses a string and treats part of it as control syntax, then you must separate untrusted data from the control syntax so the interpreter cannot confuse them. Parameterized queries are a strong example of this separation because the query structure is fixed and the values are bound as data, not as executable syntax. Input validation can help, but it is not sufficient on its own when the target language has rich expressive power and many encoding tricks. Output encoding is relevant in some injection contexts, especially in markup and scripting contexts, because it changes how data is interpreted by the browser. The control theme is consistent. Treat untrusted input as hostile, keep it as data, and constrain how far it can travel into interpreters without a safe binding mechanism. Insecure design is a newer sounding label, but the underlying idea is straightforward and very important. Insecure design reflects missing threat awareness and unsafe architectural decisions, meaning the system is built in a way that makes certain classes of failure inevitable. You can code perfectly and still fail if the design assumes trust where trust does not exist, or if it ignores likely abuse cases because they were never considered. This category is not about a single bug. It is about patterns like lacking segmentation between tenants, failing to enforce business rules consistently, or allowing risky workflows without compensating verification. It also includes decisions driven by speed or convenience that remove safety constraints, such as skipping rate limits, skipping step-up verification, or building administrative functions on the same plane as user-facing functions. When you hear insecure design, think about the difference between fixing a crack in a wall and realizing the building was constructed without a foundation. Threat awareness is the bridge between design and controls because you cannot protect what you do not model. If you do not identify assets, trust boundaries, and attacker goals, you end up protecting the wrong surfaces and ignoring the ones that matter. Insecure design also shows up when requirements focus only on features, and security is treated as a later hardening task rather than as part of the definition of done for the system. Another design failure is relying on single controls with no layering, such as assuming authentication alone will stop fraud, or assuming a firewall alone will stop data exfiltration. Good design uses the idea of defense in depth, which means multiple independent barriers, so that one failure does not become total compromise. The control lesson is that secure architecture is not an add-on. It is how you shape the system so that ordinary mistakes do not become extraordinary incidents. Security misconfiguration is where operational reality collides with security intent. Misconfiguration includes unsafe defaults, exposed services, debug settings left enabled, and overly permissive security headers or policies. This is common because deployment pipelines and infrastructure templates change quickly, and teams copy working configurations without fully understanding the security implications. Misconfiguration also appears as cloud service permissions that are broader than needed, management ports exposed to the internet, or administrative consoles reachable from untrusted networks. Another repeat offender is verbose error handling that reveals internal details, which becomes a roadmap for attackers. In other words, misconfiguration is about the gap between how the system should be deployed and how it actually is deployed. What makes misconfiguration especially dangerous is that it can silently undermine otherwise good code. You can have proper authorization logic, but if an administrative endpoint is unintentionally exposed, you have created a direct path around the intended controls. Similarly, you can have strong authentication, but if session cookies are misconfigured, an attacker can capture or reuse sessions more easily. Configuration drift is a big contributor, where the system begins secure but changes over time through incremental updates and hotfixes that are not governed by baseline standards. This category is also where hardening guidance lives, such as minimizing exposed services, disabling unnecessary features, and enforcing secure defaults in reusable templates. The control message is that secure configuration is not a one-time activity. It is an ongoing discipline that must keep pace with change. Vulnerable and outdated components are a reminder that modern applications are assembled, not handcrafted. Most systems depend on third-party libraries, frameworks, containers, and services, and those components carry their own vulnerabilities and life cycles. The risk is not only that a component has a known vulnerability, but that teams may not even know which components they have, which versions are deployed, and where those versions are running. Unmanaged dependencies create blind spots, and blind spots are where attackers operate comfortably. If your build process pulls dependencies automatically without governance, you can introduce risk at the speed of automation. This category is especially important because it turns external events, like a disclosed vulnerability, into internal urgency, even if you did nothing wrong directly. The failure modes here include running end-of-life software that no longer receives security fixes, ignoring security advisories, and delaying upgrades because dependencies are tangled and hard to test. Another issue is using components from untrusted sources, or using packages that are typo-squatted or maliciously maintained, which blends this category with integrity concerns. Inventory is the foundation control, because you cannot remediate what you cannot identify, and you cannot prioritize what you cannot measure. Dependency scanning helps, but it must be tied to a real process for triage and patching, otherwise it becomes a dashboard of guilt. The control theme is disciplined dependency management, including version control, trusted repositories, and prompt remediation for high-impact vulnerabilities. Identification and authentication failures focus on how systems recognize users and maintain sessions over time. This includes weak credential handling, poor password storage, missing protections against brute force attempts, and fragile session management. Even if you authenticate correctly at login, you can fail later by issuing predictable session tokens, failing to expire sessions, or allowing sessions to be replayed across devices and contexts. Another common problem is improper handling of multi-factor authentication, where the second factor is optional, easily bypassed, or not enforced for sensitive actions. Credential stuffing attacks exploit reused passwords, so systems must anticipate that many valid credentials will be tested at scale. This category is not about blaming users. It is about designing authentication and session controls that assume attackers will try to automate account takeover. Session handling deserves special attention because sessions are the practical representation of identity after authentication. If session cookies are not protected with appropriate flags, they can be accessed by client-side scripts or transmitted in unsafe contexts, increasing exposure to theft. If the application does not rotate session identifiers after privilege changes, an attacker can fixate a session and then write it into higher privilege states. If logout does not invalidate tokens server-side, sessions can remain valid longer than intended, especially in distributed architectures. Authentication failures also include insecure recovery workflows, such as password reset processes that rely on weak knowledge-based questions or predictable tokens. The control message is layered identity protection, strong credential storage, strong session semantics, strong rate limiting, and careful handling of recovery and privilege transitions. Software and data integrity failures address a different kind of trust problem, whether the system can rely on the code and data it consumes. This includes untrusted updates, pipeline weaknesses, and situations where code or configuration can be modified without detection. In modern environments, software is delivered through automated pipelines, and those pipelines become high-value targets because compromising the pipeline can compromise downstream systems at scale. Integrity failures also include scenarios where serialized data is trusted without validation, or where the application accepts signed artifacts but does not verify signatures correctly. Another angle is configuration integrity, where infrastructure templates and deployment manifests can be altered to introduce backdoors. The core idea is that an attacker does not have to break your application logic if they can change what your application is. Controls for integrity focus on verifying what you run and what you deploy. This can include cryptographic signing of artifacts, enforcing trusted build steps, and ensuring that only authorized identities can modify release outputs. Separating duties in the pipeline matters because it reduces the chance that one compromised account can both change code and approve deployment. Monitoring changes to critical repositories and build configurations is also important because pipeline attacks often leave traces in version control history and build logs. Secure defaults in continuous integration and continuous deployment processes can prevent accidental exposure of secrets and reduce the chance of unauthorized code promotion. The control theme is to treat build and deployment systems as critical assets because they effectively define the behavior of production. Security logging and monitoring failures are less glamorous than exploits, but they are often the reason incidents become disasters. If you cannot see what is happening, you cannot detect misuse, and you cannot respond quickly enough to contain damage. Logging failures include not recording important events, recording them without context, or storing them in a place where they are not protected or not reviewed. Monitoring failures include having alerts that are too noisy to trust, or having none at all for high-risk actions like privilege changes, authentication anomalies, or unusual data access patterns. Another failure is not correlating events across systems, which is necessary in distributed architectures, where a single user action touches many services. In short, logging and monitoring are controls that turn security intent into operational reality. The effectiveness of logging depends on quality and governance, not just volume. Logs must capture who did what, when, and from where, and they must do so in a way that supports investigation without leaking sensitive data. If logs capture secrets, you create a new breach surface, so logging design must balance detection needs with confidentiality requirements. Retention matters too, because short retention windows can erase evidence before an incident is discovered, especially in slow-moving intrusions. Monitoring must also feed response processes,
because detection without response is just anxiety with timestamps.
The control message is that visibility is a security control, and it must be engineered and operated with the same seriousness as access control and cryptography.
Server-side request forgery is a category that highlights how server connectivity can be weaponized. Server-side request forgery occurs when an attacker tricks a server into making outbound requests that the attacker controls or benefits from, often reaching internal services that are not directly exposed. This is especially relevant in cloud environments, where internal metadata services and management endpoints can be reachable from the server but not from the internet. The attacker uses the server as a proxy, leveraging its network position and trust relationships to retrieve data or perform actions. The pattern often starts with a feature that fetches a uniform resource locator, processes remote images, validates links, or integrates with external webhooks. The risk is that what looks like a benign outbound fetch becomes a tunnel into internal networks and sensitive endpoints.
Controls for server-side request forgery focus on constraining where the server is allowed to connect and how it handles outbound requests.
Input validation matters, but you have to validate more than just format. You have to validate destination, resolution results, and allowed protocols to prevent bypasses through redirects and alternative address representations.
Network egress controls are powerful here because they limit which destinations can be reached regardless of application logic, providing a layer that does not depend on perfect code. Timeouts, response size limits, and disabling unnecessary protocols reduce the impact even if some request is made.
You also want to protect internal metadata and management endpoints with additional barriers, because those endpoints can turn a network pivot into credential theft.
The control message is that outbound behavior is part of your attack surface, and it must be governed like inbound behavior.
As we step back and connect these categories to controls, the key is recognizing that controls are not one-to-one with categories. They are patterns that mitigate multiple classes of risk.
Access checks and least privilege directly address broken access control, but they also reduce impact in authentication failures and limit what compromised components can do. Validation and safe binding mechanisms, such as parameterization, reduce injection, but they also help with server-side request forgery by constraining destinations and inputs. Hardening and secure defaults reduce misconfiguration, but they also support cryptographic safety by enforcing strong transport security and secure cookie handling. Monitoring strengthens response across all categories because it gives you the feedback loop that reveals where controls are failing. When you design controls as layered patterns, you get resilience instead of a fragile set of point fixes. The most practical skill you can develop here is mapping observed weaknesses to the control families that prevent recurrence. If you see repeated authorization bypasses, the control gap is not just a missing check. It is likely inconsistent policy enforcement, lack of centralized authorization logic, and inadequate testing of access rules.
If you see repeated cryptographic mishandling, the control gap may be key management governance, lack of standard libraries, and weak review processes around security-sensitive code paths.
If you see repeated dependency issues, the control gap is inventory and lifecycle management, not just a single overdue patch. Thinking in this way moves you from reactive patching to systemic risk reduction. It also gives you a disciplined way to explain to leadership why certain investments matter, because you can tie them to recurring risk patterns rather than to one headline incident. The deeper reason these categories matter is that they provide a shared language for application risk that is portable across teams and technologies. When engineers, security practitioners, and auditors use the same vocabulary, conversations become about specific failure modes rather than about vague notions of secure code. That shared language also helps you avoid the trap of arguing about tools instead of outcomes, because you can evaluate whether a tool or process actually reduces a category of risk in your environment. Over time, organizations that learn this language tend to shift left, meaning they address risks earlier in design and development rather than at the end through emergency fixes.
That is not a slogan. It is a practical consequence of recognizing patterns and building controls that make safe behavior the default. If you carry one lesson forward, let it be that recurring categories are not just a way to label problems, they're a way to build durable systems that fail less often and fail less catastrophically.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.